We just looked at the kinetic molecular theory and basic characteristics of gases. Now we're going to do the same thing for the liquids. We're going to look at the kinetic molecular theory and talk about the basic characteristics of liquids. And I'm going to highlight the places where they're similar and where they're different. Let's start by looking at the kinetic molecular theory of liquids in a qualitative way. So we know that all liquids are made up of tiny particles. We know that those particles are held closely together with weak attractive forces. These liquid particles move around with an average kinetic energy that is dependent upon the absolute temperature, and because of their motion, the particles of the liquid can slip past each other, but because they're attracted to each other, they can't move around too easily, so they have to be in close contact with each other. So we're going to describe each of those in more detail, and then we'll see what characteristics of liquids are caused by these factors. So we'll start with, all liquids are made of tiny particles. These particles can be atoms, molecules, or even ions. Most of the time they're atoms or molecules, but rarely they are ions. And that's where it differs from the gases. We never see ions in the gas phase. We only see atoms or molecules, but in liquids we can sometimes see ions, but it is very rare. It is generally at very, very high temperatures that we start to see some ions in the liquid phase. So you can melt salt, but have you ever tried to do that on your stovetop? It'll never happen. So we don't see it in normal daily life. We don't see ions in the liquid form, but they can form liquids. The liquid particles are held together closely by weak attractive forces. So recall in the gases, the gas particles were not in contact with each other, and so they had no attractive forces. They were not attracted to each other, they bounced off of each other. In the liquids, they are actually in contact with each other, and they stay in contact with each other, and they're held together by weak attractive forces. For the gas example, I said that I had a couple of people, and they were running around the football stadium. They were far apart, and they had no attraction to each other. When we look at a liquid, now those things have to be close enough together to be holding hands. And so since they have to hold hands, they have to be kind of in the same area, and they are holding hands. That is a weak attractive force. They can be broken, but it's not easily broken. Now again, we're normally going to be thinking of hundreds of these particles, billions of these particles, all holding hands, and so they'll be clumped together. And that will help us to explain some of the basic characteristics we see of liquids that is different from the gases. And next we see that liquid particles move rapidly with an average kinetic energy that is dependent upon the absolute temperature. This is exactly the same as what we saw for the gases. These particles will continue to move in a straight line until they hit something, just like we saw with the gases. So this is very similar to our gases, but the difference is that they are connected to each other, so that makes some difference in the way that they behave. So what do we know from this? We know that if we increase the temperature, those particles will move faster and faster. If we add kinetic energy, the particles will move faster and faster. And the final one states that because of their motion, particles of a liquid are free to slip past each other, but because of their attraction for each other, few of them have enough kinetic energy to escape. This actually helps us to explain several of the basic characteristics where liquids and gases are different from each other. So as a reminder, for gases, those particles could move around freely and they just kept moving. But for liquids, those particles started to move, but then they were attracted to each other so they couldn't move far. Our example was for gases that they would be not touching in any way, shape, or form, and if they did hit each other, they would just bounce off of each other. But in the case of a liquid, what happens is they're holding hands. In my example of people, they're holding hands, and they would have to stay close together because of that. They don't have complete freedom of motion. They can slip past each other, so I could be holding one person's hand, then let go of that hand and grab another one, but because there's another particle right there, I'm going to constantly be grabbing on to another particle. To become a gas, those particles actually have to let go of each other, and that takes energy. There's something pulling them in, that attractive force is holding them together. They have to break free of that to become a gas. And most of the particles do not have enough kinetic energy to escape. But if we heat them up enough, they can, because they've got extra kinetic energy. And again, we'll talk about how that affects some of the different basic characteristics of liquids. Some basic characteristics of liquids that we'll be looking at. They have a definite total volume, but not a definite total shape. They are more dense than gases. They are not compressible. They flow when they diffuse, and they expand slightly when heated. So let's look at what we mean by definite total volume, but no definite shape. If I take a tall glass of Kool-Aid and I pour it into a short cup of Kool-Aid, I'll see that it fills that container to the same point, but that it has a different shape. If I put it in a little kitty cup, again, it takes on the shape of that kitty cup. If I put it in a brandy snifter, it'll have the shape of the brandy snifter. If I put it in a champagne flute, it'll have this long, tall thing, and it'll have the shape of that. So whatever the shape of the container is, that's going to be the shape of the liquid. But notice that as I fill it, it doesn't fill it to the top necessarily. It depends on how big the container is, and we notice the liquid stays at the bottom of that. And again, that's because the liquid is more dense than the air that's in the cup, and so gases are less dense, liquids are more dense, and we'll start to see that that liquid fills the bottom of the container, but it does not completely fill it. And that tells us that it has a definite volume. However much there is, it will stay the same no matter which kind of glass I take. But whatever container I put it in, it will take the shape of that container. So that's where it's different from a gas. Both of them will take on the shape of the container, but liquids have a definite total volume. They don't necessarily fill the container. And as I just stated, liquids are more dense than gases, and that's why we see in the container that the gas will be on top and the liquid will be at the bottom. Why are they more dense? Well, again, we notice that in the gases, these particles must be far apart and they're bouncing off of each other, whereas in the liquids, they are in contact with each other. To be in contact, they have to be closer together, and so that means that they are more dense because there's more particles packed in the same volume. And our next characteristic, the liquids are not compressible, and that is the opposite of gases, which are highly compressible. So in the case of liquids, these particles are already in contact with each other, so they don't compress very much. They're hard to push together because they're already in contact, and since they have to stay in contact, they can't really change how close together they are. Now, as you know, if you're holding hands, you can stretch out a little bit and you can get a little bit closer, but it's very minute amounts compared to the gases, which can move around freely. And so we say that they're not compressible, but in all honesty, there's some minor compression. But again, it's so small that we would say that it is not compressible. And we can also see that liquids can flow and diffuse, which is the same as what we saw for gases. So in this case, the liquids flow similar to a river. If it's going in one direction, it just keeps going in that direction. That's because the particles move in straight lines until they bump into something. When those particles bump into something like a rock or something like that, then they start to spread out and we say that they are diffusing. So we can see that liquids can both flow and diffuse. If you put a drop of food coloring into water, you'll see that that drop will spread throughout the liquid. And so we know that it can diffuse even if it's not flowing. Those particles do diffuse, which means, again, spreading out. They bump into each other because those particles are constantly in motion. They're bumping into each other and spreading out. And our final characteristic is that liquids expand slightly when heated. Remember, with gases, they expanded greatly, so there's a huge expansion because there's no contact. But in the case of liquids, because the particles have to be in contact with each other at all times, they do not expand very much. And again, you can think of this like when people are holding hands. If it gets hot, they're going to want to start to spread out because they're moving a little bit faster. They're going to start to spread out. And as it gets colder, they're going to get closer and closer together. And so that's what we see with the liquids. They can spread out a little bit, but because they still have to hold hands, they can't spread out very far. In the gases, they have no contact with each other, and so they can spread out very far from each other. We can see then that the kinetic molecular theory of liquids leads to the basic characteristics of liquids that we see here.